the form of representation of the language here is a DFA, a regular language. Then you're currently working on your parsers that take as input tokens and generate what you're calling the AST, a syntactic structure. Then the semantic analysis augments this tree with information around the meaning, so meaning and type information for the variables. And we also generate intermediate code at this point. That's what we're going to be looking at today. And then, of course, the output of the intermediate code is what is fed to the code generator, which then generates the final target language for the specific architecture. There's also the optional code optimization stage, which we'll see that you can either go straight from intermediate code to the target code, or you can perform code optimization on the intermediate code and then generate the final target language. So remember, we started with this diagram. So we have the three representations. There's a source language, then there's an intermediate language, and then there's a target language. So far, we're not going to be looking at the intermediate code generator, which translates our source language into an intermediate code. So we're going to look at what is this intermediate code and how is it generated. So other words for intermediate code, you can refer to it as intermediate representation. You'll find it also referred to as intermediate language. And basically the code is what sits in between the front end and the back end. So it joins together the front end and the back end. It's pretty significant in the sense that it lies in between the two representations. It's not so close to the source language, neither is it so close to the target language. So what is intermediate code? We said it's a layer that sits between the front end and the back end of the compiler. And you think of it as a simplified assembly language. So right now, I guess, are you doing, no, you did that in second year. Or when did you do assembly language programming? To the second year Unity, if I'm not mistaken, right? So you're familiar with assembly language. So intermediate code is actually a simplified assembly language that is easy to create and easy to convert to other assembly languages. Yeah. So we start with the source code. We have our abstract syntax tree. So we could actually just go straight to assembly for a specific architecture. So it could be Java bytecode, it could be Intel assembly, etc., etc. But we realize that this, in practice, is not how compilers are built. And we'll be seeing why, in fact, we need to introduce intermediate code. So we're asking, why can't we just go directly from our AST to the specific assembly language? Why do we need this intermediate language? So you can imagine if you want to do optimization, which always happens actually, that the first code you generate from the tree will be seeing it's not optimized because it's being generated as it traverses the tree. So you need another pass, which is going to look at the code which has been generated and see how to optimize it to make it more efficient, eliminate redundancies, etc., etc. So if we just go from the source code, then kind of get our AST after semantic analysis, and then come up with the specific assembly languages for the different architectures, then you'd have to get Java bytecode and then you optimize it. Or you produce your Intel assembly and then you optimize it, right? So looking at this, it's not the most efficient way to do optimization. So the role of the intermediate representation is that it should sit before you come to the target language so that you can perform architecture-independent optimizations on the intermediate language, and then you can then translate the optimized code into the specific architectures. Okay? So this is why we are adding intermediate code. I've explained it helps us do this. So if we add in intermediate code, it means that from the AST, we generate intermediate code. And of course, at this point, it's still just reflecting the source code. And then now instead of generating Java bytecode directly from the intermediate code and then optimizing it and then doing the same thing for the next architecture, we see that we can now take advantage of making our compiler easier, that you don't have to do optimizations for each architecture, but rather we can now do the optimizations on the intermediate code. Okay, so you have your AST, generate intermediate code, then optimize the intermediate code. So you only do an optimization once, and then you render that into the different target assembly languages. Yeah. So it makes it easier actually to write your compiler, that you're not having to write a compiler that is going to try and take your AST and optimize it for Java bytecode. Take the same AST and optimize it for Intel assembly, etc. So you're just going to have optimization done on the intermediate code, and then you render. So it makes it actually easier and more efficient to generate different assembly languages from the same intermediate representation. So intermediate code is another representation of the source language. It is language neutral. It is machine neutral. So it's not tied to any specific architecture. It can take many forms, and we'll be looking at some of them. And the complexity of the representation depends on how it's being processed. Yeah. So, and we'll be seeing that basically intermediate language, there's a representation which is very close to the source language, and there's another representation which is very close to the target language. Yeah, so it depends on how we choose to process or to generate it. You can have more than one intermediate language being used by a particular compiler, but the whole idea of the intermediate code is to get the program closer to machine code without losing information from the source language, which is necessary for optimizations. That's something that is going to guide us into what are useful optimizations that could be done to ensure that the code that is being generated is as optimal as it could be. So intermediate code ranges in terms of complexity. We have on one end the high level representation, and on the other end we have the low level representation. So the high level representation of intermediate code is closely coupled to the source language. So you'll see that it expresses, or it resembles, it really looks so much like the source language, only that it's a bit more simplified. It is therefore easier to generate from the source program because it's directed from the source program. However, the downside is that it's not possible, the optimization is not so obvious because the representation is still very abstract. Yeah? We're not having a fine-grained representation of the source, so it's not easy to see maybe where variables are storing the same value, and we can then condense them, etc., etc. So the other continuum is the low level. So as you'd guess, this one is closer to the target language. Yeah, so it's closer to the target machine. It expresses the low level structure of the program. It is easier to generate target code from the low level intermediate code, but as you'd imagine, the downside is true, that because it's so much closer to the target language, it becomes harder to generate it from the source language. So it's always a trade-off. You choose high level, easy to generate from the source language, harder to generate the target language and do useful optimizations. If it is closer to the target language, easier to generate the final target language code, machine code, but harder to generate from the source language. So it's always a trade-off. So this is examples of how intermediate, the different levels of intermediate representation. And you can see this is the high level representation, and you can see it kind of really looks like the source language. So you can say here we're doing an assignment. We're saying this is an array, I, j plus 2, and the value of that is assigned to T1. Okay, so this is a representation, and you can see it really resembles the high-level source language statement that you'd expect to see that the programmer would be typing. Then on the other end, we have the low representation. And you can see here, it is so much closer to the target language. We're using the frame pointer. We are using registers, you're talking about register 3, right? So it's much closer to the target language. Then we have what is sort of in the middle. So it has a bit of constructs that are inspired by the source language, but also a bit more closer to dealing with the physical machines in terms of VNMB, how we introduce the temporary variables to represent our registers. Yeah, so we'll see that most probably we'll end up just sticking with something in between the two extremes, so that it's not too hard to generate from the source language, and neither is it too hard to generate the target language from the representation that is chosen. So as you can see here, we're basically just saying j plus 2 goes to a temporary variable 1. Then we compute T2 as I times 20. Then you add T1 and T2. You're basically trying to get the address of a memory location and assigning it or something like that. So you're going to see how do we then generate intermediate code. So before we do that, what makes a good IC? IC is just intermediate code representation. First, of course, it should be easy to translate an abstract syntax tree into, and then it should be easy to convert it to just about any assembly language. So that given an AST, it should be straightforward to generate intermediate code from that AST. And then once you have the intermediate code, then it should be easy to render it into most of the common assembly language representations. So what does it entail to have a good IC? So number one, we need to have as few commands as possible so that you don't have too much choice, so that the commands are pretty powerful in terms of the complexity of the operation that can be performed, but they are few. But they should be complete in the sense that you should be able to express any kind of computation using those few commands. They should also be designed to make it easier to do common optimizations, and we'll be talking about code optimization after we talk about code generation. So I remember we were saying that we want to optimize the intermediate code before we then generate the target language, assembly language representations. We also want flexible commands that make it easy to identify what is being done. And once you know what the operation is trying to achieve, it becomes then now straightforward to, as you're rendering it to the next assembly language, to know which instruction to map the intermediate code instruction onto the instruction set that we're using for whichever assembly language we're using or we're retargeting to. So most important is that the intermediate code operations should not be tied to a specific architecture or a specific machine, because then portability becomes a challenge when you want to port to a different architecture. That's why we say they're machine independent and programming language independent. They try to be as neutral as possible, making it easy to render. And of course, that's why we're saying the challenge is if it's neutral, there could be some features you have in language A that you don't have in language B, or a certain processor may have some feature you can take advantage of that is not in the other processor. But once you choose this interface of commands, that's what we're saying, it should be complete, but not tied to any architecture. Then now the challenge will be, as you're rendering to a specific architecture, to understand what the intermediate code instruction was trying to do, and then do the proper selection of the instructions and optimizations that are needed for the specific assembly language that you're rendering to. So how do you represent intermediate code? So there are three different, of course, we have the textual representation, and that's what we're going to focus on. But then there are also graphical representations. So of course, we know about the AST because that's coming from the pass tree from the scanner. So here we retain the structure of the pass tree as it was generated. We will eliminate unneeded nodes, and we'll be showing you how to do that. And in this case, we know that the nodes represent operators, and the children of the nodes are the operands. Yeah, so that's just one way. So we add more information onto the AST, that as we're traversing the AST, we're generating the intermediate code for each node or child of the tree. Another representation is what is called the directed acyclic graph. And this is just the AST, but it's compacted in the sense that we remove redundancies. We remove duplication. So common sub-expressions are represented by a single node. And why we want to do this is that you end up generating fewer, a much smaller intermediate code, which is what we want, so that it translates into a more compact target language machine code. Then we also have the control flow graphs. I know you've come across the acronym CFG before when we're talking about grammars. So CFG also has another meaning in the compiler jargon. It's basically known as a control flow graph. And we'll be looking at that later in the next topic, how we use it to model the flow of control within the program, because that's something that we need to be able to generate code that determines how execution will be passed from one maybe function or part of code to the next. So this is an example of the AST on the left and a compacted AST, which is what you're calling the directed acyclic graph on the right. So if you look at our statement, we're saying A is assigned B times minus C plus B times minus C. So these two sub-expressions are actually identical. Yeah. So unfortunately in the AST, we'll treat them separately as we traverse the tree, because we'll have to come up with a tree to accept the entire string. And this means that you have to generate intermediate code for this 2 times, even if they're the same. Now, when talking about the DAG that compacts and removes duplication or redundancies, so once you realize that actually this is exactly the same thing, you just condense them into or collapse them into one node. Here, basically, you're saying that the operands for plus is the same thing. So this means you'll only need to compute this once, you'll only need to allocate memory once, and you just copy the answer. Once you have this, you just use it again to do the plus. So this will result in a shorter, in a more compact intermediate code, and consequently a more compact target language code. Yeah, so these are just examples of the graphical representations of the intermediate code. And I talked about the linearized representation or the textual representation, and this is actually what is more common, like what you're going to focus on even as you're doing your project. So here there are 2 types. There's what is called stack-based linearized IC, as well as 3-address code. And 3-address code is what is most used. So this is what I want you to familiarize yourself with. And why it is preferred, the 3-address code makes it very easy to do optimizations. And remember, optimization is so critical for compiler design. So we chose a representation that makes it easy to identify what needs to be optimized. And the 3-address code is what comes out on top. Why is it called 3-address code? Because it can allow for at most 3 operands per line of intermediate code. So two operands and 1 for the result. Yeah. So they also refer to as quadruples. So in here, 3-address code or quadruples, they mean the same thing. So we say there are 2 types of linearized IC. So one is a stack-based, which is compact. So in this case, you're basically just saying, just push 2 onto the stack, push 1 onto the stack, multiply the things at the top of the stack, then push X, do subtraction, etc. But the 3-address code is easier to see what is going on. And as I said, it makes it easy to identify the optimizations that need to be done. So in this case, we're saying 3-address code or quadruples. They allow at most 3 operands and 1 operator. So note that 3 operands and 1 operator. That's why they're quadruples. So in this case, we're basically saying the value of 2 is put in the temporary variable 1, value of y is put into temporary variable 2, Then we multiply T1, what is in temp 1 and temp 2, and store the result in temp 3. Load the value of x into temp 4, and then T4 take away T3, load the result in T5. So you can see at most you have one operator, and at most 3 operands, including the result operand. So I want us to focus a bit more on tree address code. So we say the format for a typical command is something like A equals B operator C. So basically we have the operator, the result, and the 2 operands. Yeah. So it's a quadruple, and represent them in this format. Yeah. So you put it in brackets. So you have the operator. So they're saying apply the operands for this operator is B and C, and the result is in A, because this is what we are translating into quadruples. So for example, if we have this as a high level representation of the instruction, we now want to represent it using quadruples. Yeah. So here we can see we need to first, from the tree, we'll end up doing first B plus C. And then we need the other operand for the times. And then we're going to say T1 times T2, because we've loaded T1 and T2 with the values that are needed. And then we assign the value of T3 to A. So this is actually how we now write them as quadruples. So remember, the format is the operator, the result, and the operands. Write it as it's a plus. So we have the operation, binary operation, add. The result is T1, and we're adding the operands B and C. So add B and C and store in T1. Then we have unary minus. The operand is E, the result is in T2. We have times or multiplication. So we take T1 and T2 and store the result of times into T3. And then finally, an assignment operator, an assignment operation. So T3 is assigned to A. So note that when we're doing quadruples or tree address code, or in general intermediate code, we generate lots of temporary variables. So T1, T2, T3, etc. And we generate them as many as are needed for our logic, for us to store the results of, or the intermediate results of computations. So the types of operators we have binary expressions, we have unary expressions, we have jumps. So examples of binary expressions we can have math, so addition, subtraction, multiplication, division, etc. We have logic expressions, so B and C, or B or C. Also relation, A equal to B, etc. So all those are binary operators. We have unary operators for math. Of course, we have minus and a sign. For logic, we have not. For memory, we have getting the address or allocating memory. Then we have jumps. So you create a label, or you go to a label, or you can also have a conditional jump if a value go to a certain label. So you can see, we said even if they have few intermediate code instructions, we said it should be as complete as possible, meaning that we're able to translate anything in the source language into the intermediate code representation without losing what the programmer intended. So we probably know Spin. I don't know what platform did you guys use for assembly, your assembly course? What processor and which assembly language were you using? Or you didn't do the course? Mm-hmm. Were you all in the same, or you were allowed to just choose whichever platform you wanted for your, or even what kind of projects did you do in that unit?
We just had, we're told to use the Nasm compiler and you didn't make a project really, but you are given assignments.
Please speak up, Dominic. I can't hear.
Saying you are never given any projects to build in assembly, but you are given assignments to do
Mm-hmm.
on that particular architecture.
Okay, I hardly had, but thank you for the response. I had at least you didn't have a project, but you had assignments to do. Okay, so at least you're familiar with assembly language programming. So SPIM is one of the most, it's a relatively common simulator for the MIPS32 assembly language program. So I don't know which one you're using, but this is, and you can relate as we go through this, you can now relate to the assembly language that you are using. So this is a commonly used simulator for the MIPS32 assembly language program, and you can actually generate SPIM commands and then run them on SPIM, and you basically just look like you're executing an assembly language program. So SPIM uses a 3-address code to represent instructions, and we'll just be using a few examples from SPIM to just explain how intermediate code looks like and how we actually use it. We said and we're using kind of the medium, not too close to the source language and not too close to the target architecture. So in this case, we're doing like you want to do a load or a store from memory. We have a command in SPIM that is just LW, load word. So moves the value that is located in the given address into a register. We can move a constant into a register using the li command, and LA moves the address of the variable into the register. Then there's store word, which is basically stores the value from the register into memory. So it has a simplified instruction set. So these are examples of SPIM commands. So load the value 5 into register T2 is as shown. Then LW T3, X loads the value stored at the location labeled X into register T3. You can load the address of the location labeled X into register T3 using the LA load address, and so on and so forth. So it allows us to do stuff like this. So we want to be able to generate intermediate code that looks like this. So SPIM uses a lot of registers, or rather, remember you're coming up with intermediate code that should work for any architecture eventually when you translate into the target. So SPIM allows us, we have a big choice of which registers to use, but of course, you don't want to choose like maybe until 32 registers, because then you're forced to. It will be hard for you to translate that code to a processor that has maybe 16 registers. Yeah. So what most intermediate code does, it just forces you just choose a subset of available registers, maybe like 8, because maybe that's the minimum that you could find in any architecture. At least you find every process at least 8 registers that you can use for computation. So you reserve 8. So you say all your intermediate code will only refer to 8 temporary variables, where of course each temporary variable is going to be mapped onto a register when you're now doing the target code generation. Then binary arithmetic operators, the work is done in the registers. So in this case, you can load operands into the 2 registers or even a constant. So those are the commands. So add what's in reg 2 into register 3 and store the results in register 1. So be able to do the operations within the registers. The other thing is like for unary operators, that would be the format. You basically say the contents in register 2, negate them and store them in register 1. So intermediate code operands, of course, it depends on the kind of operation that we are performing. So they can be program variables, they can be values at memory locations, which we enclose with square brackets. They can be constants or literals, and they could also be temporary variables. So we're allowed to use any of those as operands for the intermediate code instructions. Temporary variables, as I said, these are created on the fly, and they're used to store intermediate values. And we need them because intermediate presentation is not as expressive as high-level languages, where you're going to create as many variables as you want. So here we just store intermediate results. Like if you're doing a times and a plus and all that, you're going to do it step by step, and each step you're going to create a temporary variable to store an intermediate result, which you then use in the next instruction and next instruction. So you'll end up having very many intermediate code instructions, and that's why we must do optimization before we now translate it into target language. So let's look at an example code of using quadruples, a three-address code to convert a high-level statement. So in this case, we have an if statement. So if A is less than B, then A equals 1, and we end if, right? So when you do the A equals 1, if A is less than B. So the logic we would be using is this. So we'll assign the value of the logical operator less than to temporary variable 1. So A less than B, so it will, T1 is a Boolean value, either it's true or false. Then we negate whatever is in T1. If and we negate it and store it in T2. So if T2 is true, that means that A was not less than B, it was false. And of course, if it's false, we don't want to execute this instruction, we want to jump. So we say if T2, then go to L1. If T2 is false, it means this was true. And that means now we come and execute this, because we don't jump. We jump if it's the case that we do not want. And why are we doing this? We're doing this because intermediate code most of the time doesn't have the else instruction. So we have to reorganize the logic to implement the else. So the equivalent representation in quadruples is less than A less than B, so the result in T1. Negate the value of T1, store it in T2. If T2 is true, jump to L1. And then L1 now you continue. If T2 is not true, you just continue here. You want to jump, you will just continue sequentially. You do the assignment. I hope you followed that. So if we have an else, so we're saying if A is less than B, A equals 1, else A equals 2. So in the same way, the logic would apply to do this is as before, we check if A is less than B, so the value in T1, negate that value. If it's true, it means this was false, so we want to come to the else. So we're going to go to L1, and L1 is where we assign A equals 2, and then proceed into the rest of the code. If T2 is not true, it means this was less, so we want to come and execute A1. So it will just sequentially go to A1. Once you're done with that, you need to skip the else part, so you go to L2. And this is the equivalent quadruples representation. Okay. So this is another example. So in this case, the operand for the less than operator is also another expression. And so we first need a temporary variable that stores the result of B plus 7. So T1 equals B plus 7. Then now from there, we check if the value of T1 is greater than A, and then we proceed. So in this case, we are using more temporary variables. And you can see the equivalent quadruples. So we ask you to come up with quadruples for a particular statement. So we would expect you to do it like this. Yeah, because the quadruples, you have to put them in brackets, start with the operator, then the result, and then the operands. Okay. So I'll want you to come up with the quadruples for this fragment. So int x is equals to 3, while x is less than 10. You want to increment x, and then of course you stop once the condition is false. So could we challenge ourselves to come up with the quadruples for this? I'll give you 5 minutes or less, like 3 minutes. Okay, I hope we're done. I've seen Craig, you are writing something. Could you walk us through your solution? And we wanted quadruples, Craig. So remember, quadruples are this format here on the right.
Hello, can you hear me?
Yeah.
Yeah, so what I did is I assigned X. I
In a
assigned
very noisy place. Or is it Bryson? Could you mute yourself?
actually I am near Bryson. I'm using Bryson's microphone. My microphone
Okay.
is not working.
All right.
Yeah, so the first thing I did is I assigned 3 to X, and then I create a temporary variable for the boolean which is being evaluated, which is being used by the while loop. So
Mhm.
T1 X is less than 10. Then I've seen the pattern of you do a negation of that logical expression. So that is T2. So L1 of, I think now for L1 I used an if statement to implement the while loop. So if T2, that means the expression in the while loop is false, it should jump the body of the while loop. But if it is correct, then it will go to the next line, which is x is equals to x1. Then the reason I have the go to L1 is to do the while loop again. Then L2 is down there.
Mhm. Okay. So could you translate that into quadruples? Because the question wanted quadruples.
So to quadruple, so for quadruple,
So like the first one is an assign. You'll have open bracket assign x3. But it's okay. I think because the logic is okay, we can just look at what we have the solution on the slide in the interest of time. So thank you, Craig. So this was our question. Yeah, so something like that, I think, is what Craig had. Although in my solution, created an extra temporary variable to store the addition of the counter, the x. So assign x3. Then we have a label. I know Craig had joined your label with the if statement, because at what point you have to keep checking if it's less. So T1 is 2. We check whether X actually, had you done that, Craig? Did you check all the time? Let me see what you had.
no I didn't.
Yeah, I've just realized that. Yeah. Yeah, because you need to check because it's a while loop. You'll only get into the while when the condition is true. Yeah. So T1 is X less than 10. We negate it. Then now we check. If false, we go to L2. That means we jump the well, the body of the well. If our condition has been met, we then come and increment. We've created a temporary variable T3, which now stores the value of x plus 1. And then we reassign x to T3 and then go to L1. So you come back here and then you keep checking. So we need to be able to check every time so that we exit the while loop when the condition, when x is not less than 10. So this is the equivalent quadruples. So this is what I would want to see. So you may start here, but ultimately quadruples are in this format. So I hope it's clear. Now, we're saying we're starting from the tree to generate intermediate code. So how do we translate the abstract syntax tree into intermediate code? So there are many complications that will be encountered. One is that if we have nested language constructs, and of course we will have nested constructs, we need to figure out, we have to sequence the code to make sure that it is matching the source language representation. So for instance, it might have a while that is nested within an if statement, or vice versa, or even a while nested within a while. Yeah, so you need to be able to keep track of nested constructs. So we need an algorithmic way to be able to translate the AST into IC, because you're not going to do it as a human being. Remember, it's an algorithm that you're going to write, which you are also going to write, because the last part of your project is to actually generate intermediate code from your parse tree. Okay, so you need to figure out, how do I do that? And we're saying there's an algorithmic way we do that. So you have to come up with a translation strategy for each node on the tree. So that for every node, then you'll be able to say, this a node that is of this type, these are the intermediate code instructions that we generate. So from each node, we generate a sequence of intermediate code instructions. So the algorithmic way to do this, to translate our AST into intermediate code, you'll start from the AST representation. You're going to traverse the tree and then define a translation for each node in the AST. And of course, this is going to be guided by the grammar that you have, right? Because even the tree is being generated from the grammar. So you'll be able to anticipate the different types of nodes that could ever result in your tree, and then ensure that for any type of a node, we have specified the kind of the sequence of intermediate code instructions that should be generated. And then you recursively translate the nodes as you traverse the tree. So it's not so difficult to do. So notation that is used, we use the double square arrows to enclose the intermediate code. So for instance, if we have the language construct E, it's in ICs enclosed in square brackets, double square brackets. And we know that actually E could be made up of multiple intermediate code instructors, as we're going to see. If E is an expression, then we know that we can reuse it as an operand or an input to another instruction. It may represent a value. So we can also have a construct such as T is equals to the result of the particular intermediate code expression that we get. And this allows us now to reuse the results of one node to the higher node. For instance, we're saying plus operand A, operand B. When we compute that plus, we know we can do something with it in the higher level of the tree. So allowing us to do this is important, where we assign a value to the code of a particular construct. For a variable v, we basically just call, we're saying t is assigned the intermediate code for v, which is the value of v. And we're basically assigning the same value. We are copying the value from the variable to the temporary variable t. So with that notation, how do we then generate or translate our nodes, the AST nodes, into intermediate code instructions? So if we have binary, I remember we're saying we need a strategy for each type of node that we can anticipate. So we know that we can have binary operators, we have unary operators, we have jumps and labels and go-tos, conditional go-tos. So for each type of thing we can anticipate, we need to show how to come up with the code. So for binary operations that take the form operand 1, operator operand 2, and the result is stored in T, we expect to see something like this, that T is equals to the intermediate code for expression 1, the operator, and the intermediate code from expression 2. Okay. So for instance, if this is our AST, we have operator, let's assume it's add, operator, maybe add E1, E2. We're going to generate IC that is of this form. So the first thing, we are going to generate the intermediate code for this construct, and it will be a sequence of intermediate code instructions enclosed in double square brackets, and we assign that to temporary one. So temporary one equals the intermediate code of this thing, the result of this thing. The same thing with T2. And then now when we want to do this operator, then we'll basically say T equals T1 op T2. Yeah, so this now becomes a sequence of intermediate code instructions that we generate for this part of the tree. For unary operator, and this is what we're saying the strategy, given the different types of nodes we expect to see, now this is an algorithmic way to do this. So you just get the IC for this, the IC for this, and assign it to a variable where this is the operand. If it's a unary operator, you get the IC for this construct and assign it and apply the unary operator to it and assign it to a temporary variable. So supposing we want to come up with the intermediate code for the short circuit OR. So we have this OR operator, for instance, in C and C++. We're saying the intermediate code T will be the intermediate code for expression 1, short circuit OR, expression 2. Now, what are the semantics for short circuit OR? So we say you evaluate expression 1. If it's true, we are done. We return that as a result. Else, we evaluate expression 2, and that becomes the result. So this would be the equivalent IC code that we generate. So first, T will be expression, the intermediate code for E1. If T, we go to L1, we are done. Else, you go and evaluate. T will be the result of evaluating E2. Okay. So this tells you that for each type of operator that you have in your grammar, you'd have to figure out how to generate the sequence of IC code for each of them. What about short circuit AND? So evaluate E1. If E1 is true, then evaluate E2, else we're done. So can somebody give us the equivalent 3 address code for a short circuit AND instruction? So I just want you to copy what we did. Sorry. I want you to just copy what we are doing here. And then you do the short circuit AND. Anyone? Do for us the short circuit AND. You guys are silent. Neville, can you do for us a short circuit AND? Okay, if you guys don't want to attempt, huh? Neville, you want to attempt it? Yes, Abdiladif.
So let me try. You can say the first T1 equals to expression 1. And
Why
then,
don't you type it out, like on the chat or something?
okay. Well, I am done.
Okay. So thank you, Hassan. Yeah, but remember, you've seen the semantics, yeah, of the short circuit, and we only want to evaluate E2 if E1 is true. Yeah.
And we calibrate to say if T1, then we go to an L1. Let me try.
I can see Jeremy has made an attempt, but
There's one thing I have to correct in the end.
mhm. So Jeremy, are you correcting? Anyway, I think you guys can do that. So you test yourselves. You've figured out what we're trying to do, and we're basically saying we have to think through all the operators that we have and figure out how to generate algorithmically the equivalent intermediate code. So how do we translate statements? Because we can have multiple statements, one after the other, which is actually how we write our programs. So if you have a statement sequence, S1, S2, Sn, then the intermediate code is pretty easy. You basically just concatenate the IC for each individual statement. So if we have our ASD looks like this, a sequence of S1, S2, Sn. You just have S1, S2, Sn, and they're concatenated into a statement sequence. So that's also straightforward. If you have switch statements, same thing, you have to figure out, come up with code that translates a switch statement from in a tree into IC. And you'll read these on your own and basically see the logic that is being applied to do that. Now, what is the issue? You've seen how what IC is and how we generate it. Already you can see number one, it may not be the most efficient because it's operating at a very local scale. It just takes a node from an ASD and it generates code and concatenates to the code of the next, either the next node or the next branch on the tree. So they're straightforward, but very inefficient. We generate a lot of temporary variables. We generate a lot of labels and lots of instructions, right? And it's because we're trying to do this algorithmically for each type of a node that we can anticipate to be on the tree based on the grammar. So the question is, can we do this more intelligently? Because of course, if you have code that has so many temporary variables, it becomes inefficient to run it, and it's resource intensive if you are just to translate that into target code. The same thing with all these labels, jumps, and all that. We know we've done operating systems. You know what that entails in terms of processor time and all that. So it's straightforward. It's easy to do, but does not necessarily give us the most efficient code. So you read how type checking works, and you need to get information from the source to figure out how best to do things. So that you're not just generating blindly within the tree, but we benefit from a global view of what the source language program is attempting to do. So we need to use the syntax of the input to generate the output. So we're going to look at declarations, because code will have declarations, will have expressions. There's the control flow. We've seen an example, for instance, of a while loop. And then there are procedure calls and returns. How do we ensure that we do not generate so many labels and jumps and temporary variables? Can we do it a bit more intelligently? Sorry, I always do that and go to the wrong place. So when we're processing declarations, we need to first, of course, understand that declarations also generate code. So when you're declaring a variable or you're declaring an array, there must be code generated to create the memory allocation, for example. Yeah. So we need to allocate memory for variables. For instance, maybe a 4-byte word for each initial value, or a large space if maybe it's a record, whatever. So whatever declaration is there, we need to figure out what code to generate so that we're able to allocate memory for the variables that have been declared. Then there's the notion of both global variables and local variables. The other challenge is also to bind names to the storage location so that we know in a particular memory location, this is the variable that has been stored there, or this is the value that we're going to reference. And I hope now you begin to see whatever you did in operating systems. I think you did that in year 2. So you can imagine now that's what you're trying to replicate, that because the operating system uses the code, that the instructions that are put in the program to decide what to do and how to allocate memory, what registers to allocate. So our code should be explicit in terms of what needs to be done, so that now the OS is able to just go ahead and carry out those instructions. Of course, based on how the system calls are handled. Then we have to be aware of the different types and what it entails. So for instance, an integer value versus a real value, how much space are we allocating? If it's a Boolean, what are we doing with it? We have composite types, which are pretty complicated. Like if somebody has defined an array or records, we need to be able to figure out how much space must be allocated. We need to be able to figure out how to reference a particular entry in that record or in that array. And this is going to be done by generating the right code for that. So the declarations are tied to generating code for expressions. So the issues we have to that have to be considered when we are processing expressions, of course, we must ensure that we're generating code that is correct. It reflects what the source language is attempting to do. Type checking and conversions should also be maintained, that we do not assign operators to the wrong value. So whatever has been done from the semantic analysis has to be preserved. We have to calculate addresses for constructed types, as I've said. And we also have to manipulate and ensure that the control flow for control structures is implemented correctly. So for instance, what we're doing like with the short circuit and or the short circuit, or the jumps have to go to the right place, otherwise you'll be negating the function of that operator, right? So you want to ensure that you're generating the right code for the right operator. So let's look at examples. For instance, how do we generate IC for expressions? So supposing this is our tree. So first on the left, we have a fragment of the grammar. So S goes to, ID is assigned to E goes to E plus E, and then E goes to ID. So what we're going to do is that as we generate the parse tree, as we pass the input token from the scanner, we'll not only be generating the parse tree, but we'll also be generating the IC for a given input. And then we're going to introduce the notion of attributes. We're going to augment the tree with attributes that help us to pass information about the variables and what we are storing in each of these variables up the tree. So for example, if we have the input is A is assigned B plus C plus D plus E, and we have now built our tree like this. So we now need to augment this tree with information that as we are generating the code, we keep track of which temporary variable is holding which result for which part of the subtree. So for example, when we come across now a leaf, a terminal B, we know that this is of course from the symbol table, we know what it is. So in this case, we're saying we're going to assign the value of B to temporary 0. And that is going to generate this, for example, in Spin. Once you come up with your tree like this, the next thing you're going to do is generate this line of code. Load word B into temporary 0. Then we come across the next part of the tree. So we're in this subtree. So we would load C into T1. So we just incrementally keep adding the temporary variables. So you have to have a counter to keep track of how many temporary variables you've already introduced. And then we'll be seeing now when we start generating code, how to reuse these temporary variables because they're not infinite, because ultimately we have to map them to registers. So you don't want to create a place where you have like 500 temporary variables and then you get stuck when you're trying to translate your IC into a specific architecture, maybe that has 8 registers. Then you get a big challenge to figure out how to manipulate your 500 temporary variables. So we try to keep them to, and as we said, at least maybe 8. Play around with that, but you need to keep track of how many variables have we used so far and which values are in which temporary variable. So in this case, we load C into T1. Then now the next thing we want to do for this subtree is do the addition. So we already know what is where. So when we are traversing this tree, then now we know we are loading T0, we're adding T0 and T1 and storing the result in T0. So the issue of reuse, because we don't want to now just create a new T2, store this in T2. We know we've now used the value, we can reuse the same operator. And we'll be seeing that there are algorithms that allow us to assign temporary variables very efficiently. So right now we're just showing it pictorially, but when we talk about code generation, we'll see the algorithms that actually help us determine when to create a new temporary variable, when to write something to memory, etc. Then we go to the next subtree. We have D, and we want to add the results of D. So we load that into D, and then we add D to the result from this subtree, which we had stored in T0. So we generate that expression. Then the same thing, we load E into temporary variable 1, and then we do the addition. And then finally, we have the assignment. Yeah, so as we're traversing through the tree, depending on the kind of operator that we have as the node, then we know we have to create temporary variables, or we know which temporary variable is storing what part of the tree, and we reuse accordingly. So you can see it's not very easy, but it is with the algorithms that have, if you understand what it is you're trying to do, then it's easy to come up with an algorithm to do it. So the other challenge we said over and above declarations is, for instance, when you're talking about constructor types, so things like records and arrays, so memory allocation and memory referencing, we also need to be sure we're generating the right code. So for instance, if the code says AJ comma, K. We need to know which memory, what does that translate to in terms of the actual memory address. Yeah. So we need to keep enough information to generate code that finds the appropriate data at runtime, especially for constructed types. So we already know about records. So here we need to allocate a block that is large enough to hold all the record fields. And of course, the large enough is dependent on first the type of values that are being stored in this record and how many they are. Yeah. Then the issue of boundary, knowing at what point this is extending until this memory location. So if I have to create, I have another declaration, where will it start from? So we have to be able to keep track of that as well. And then field names, if you need to address a specific element within a constructed type, how do we compute where to find it? What is its address? Yeah, how do we offset from where we started to store that particular record? So for instance, in SPIM, there are two ways to calculate the addresses for records. So there is just using the base address and an offset, which is the most straightforward, and also there's just the way that it is used with scalars. So for example, if we have record.b, so we want to find out b's address. So we're going to figure out what is the offset of b in the record. So we're going to load the address of the record into T0. So that is where we started to store where it has been declared to start from. You add the offset, and then you load the word that is referenced by the value in this temporary variable and store that into T1. So that way now we know how to compute the value of B and use it, because you may now need to create intermediate code that uses the value of a particular field in the record. So you need to be able to generate the appropriate code. So this I'll leave you to read on your own. What's important is to understand what are the complexities and why we need to do this. Whenever we have things we can fetch from memory, then we need to be able to calculate the correct address so that we generate the right intermediate code. So for instance, if you have an array from L to H, and each element within the array has a size S. So how do we compute the number of elements? It will be H minus L plus 1. Therefore, the size of the array will be the number of the elements E times the size of an element. So that tells you for declaration, that's how much space you have to allocate. And then the address of element AI, how do you compute it? So first we need to know the base address for the array A. So if we assume it starts at address B, then to get the address of element AI, it will just be B plus I minus L times the size, because that tells us how many elements are between I and L, and then you multiply by the size of each element and you add it to the base address. Then now we have the address for where we get AI. So that's done pictorially. And this is just an example, just following that algorithm. So if we have A is from 3 to 100, element size is 4. So the number of elements will be 100 minus 3 plus 1 gives 98. The size of the array is 98 times 4. If we want to get the address of element A50, if we assume that A starts at address 100, so it will be 100 plus 50 minus the lower bound 3 times the size of the element, 288. So we'll know that now this is the value. If we store it in a temporary variable, anytime we use that value, we know we're going to be accessing the contents of element A50. And it gets, this is how SPIM does it. And that's what I was saying, maybe depending on the assembly language you're using, there are different instructions that you came across of how to manipulate, for instance, arrays. I don't know if you did all that, but this now shows how you would do that in SPIM, generating intermediate code for manipulating one-day arrays. So of course, depending on the kind of row major versus column major, I think you've done this thing in operating systems. So depending on the method, the strategy that is being used, then you have to figure out how to calculate. So this one I will leave you to read because it's just a matter of looking at the example and figuring out if you were to now get into this element A64, 6,4. If you're doing row major, how do you compute that? If you're doing column major, how do you compute that? And that's an example. These are 2D arrays. 3D arrays, even more complicated, but the algorithm is the same. Yeah, so row major and column major. And this is the generalization. So this allows us to compute the address for any n-dimensional array and get an element from there. So flow of control, this one we've already touched a bit on it. We've looked at the while loop, and Craig did that for us. So the standard, so we are asking, because we said this is another complication that we need to address, is how do we, over and above declarations and expressions, we also have to make sure we generate the right code too for control structures. So of course, a common control structure is the while loop. So the standard translation for a while loop is we evaluate a test. If the test is true, we execute the statement within the while loop, and we repeat, we come back again and keep checking if the test is true. If it's not true, we exit. So we go to star, that means we exit from there. But because we don't have an else statement in the 3 address code, we have what we've done as the alternative translation that you've seen. You evaluate the test. If the test is false, you exit, else you execute the statement and you come back here and evaluate the test. Yeah. So you've already seen that in action. So generating the code for the for while is the same thing of concatenation. So this is just an example of how they would do it in SPIM. And we're now using this evaluate the test. If the test is false, go to outside the loop, else continue and repeat. So you can see what is happening. So you will create the beginning and the end after the statement 1, which is the while loop. And then now this is you generate the code for the expression. If the value is 0, you go to S1 after, meaning it's false. Else, you go back to the beginning and you concatenate the things in order. So this is just an example and there's explanations. And this is what you guys are now going to be doing, that as you're traversing your tree, you'll have to figure out what are the intermediate code instructions for each node. And then all you do is concatenate them. And then that just gives you the entire intermediate code representation. The if statement, this is the logic. If the test is false, exit, else, execute the statement. Then you have the if then else. If test is false, come to the else bit. Else, if it's not, you execute S2 and you exit. Yeah, so we're basically saying because you don't have an else per se, we have to be very careful when we're translating the high-level language construct that has an else. We ensure we generate logical IC instructions so that you're not negating the conditional or the loop. You're implementing it in a way that is logically correct based on the language. This is an example of a for statement. We initialize the limit, we initialize the counter. Then we have this label here. If counter is greater than the limit, we exit. Else, we execute S2, you increment the counter, and you come back here. And that is the equivalent way to generate that code for a for statement. So you're going to borrow a lot from this to help you generate the code. So the remaining bit are just examples from SPIM, and I'll leave you to read this on your own because all we want is to ensure that you've understood what IC is, why we need it, and how we systematically generate it from the AST. So we'll just look at this last example. So you remember we gave this example and said if you use an AST, it doesn't compact the code, but if you use a DAG, the directed acyclic graph, because these two are the same, it should only compute it once. Yeah, so let's take a look at this. So if you're traversing through the tree, we have B, we assign it to temporary T0, and we generate that line of code. Then we load C into T1. Then we're going to negate T1 and leave the contents in T1. So we've done B and T1. Then what we want to do now is multiplication. So multiply what is in T0 to T1. And so the result in T1. And then again, we repeat the same things for the second subtree. Store B into T0. Load C into T2. Negate, multiply. So now we have one result is in T1. The other one is in T0. Then finally, we do the addition. And then lastly, the assignment, where we store the value that is in T1 and assign it stored into address that is located, referenced by that variable A. So of course, you notice that if we use the directed acyclic graph, we don't have to do all this second bit here because we know that we've already computed this. Yeah, so we're just going to reuse the instructions. And you can see that's what happens here. You load B into T0, C into T0. No, this should be T1. Then you negate, and then you add. So load B into T0, load C into T1, negate T1 into T1, multiply T0 and T1 and store in T1. And then now, because we know it's the same, and we're doing addition, so you basically just add T1 into T1 and you store it in T0. So here we've gotten rid of the repeated instructions because of using the DAG. And then finally you do the assignment. So I'll leave you to read all this, look at these examples. This is specifically for SPIM, but should give you ideas on how to do this stuff until the end, okay? So I'll share this. This brings us to the end of our class for today. So this is an example, a screenshot of running SPIM on the code that is being generated, and you see the assembly language instructions being processed. Okay. So we'll end there. You'll read this on your own. It's basically explaining how SPIM does the concepts we've looked at. And now your next challenge after you do your syntax tree, your parse tree, is to figure out how to translate your syntax tree into intermediate code. Yeah, we're going to just choose, you already chose very simplistic mini language, so you don't have many operations, you don't have many loops. So that will be the last assignment I give you, that from your AST now, you'll be able to see the intermediate code. And if you're ambitious enough, you could target the same processor you used for assembly language course. So once you generate your intermediate code, you can try and see if actually it does run and does what you have, what your original program was doing. Great, we'll end there. So tomorrow I am attending a workshop. I won't make it for tomorrow's class. So you're going to use that time to continue working on your puzzles. I had Taylor at the beginning of the class. Clearly you guys have not even started working. So I hope you're taking your work seriously because I don't think it's due next week if I'm not mistaken. So you need to really step up on the amount of time you're giving this bit because you're going to do the same demos as we did for the scanner. So end of class. Enjoy the rest of your afternoon.